coming up on 10 a.m. Portuguese time, so it's time to restart. Hope you all have a drink of water and stretch your legs. So the next thing to think about are the bonded forces. Those two are a unit of concurrent work that can be offloaded. These two are a piece of concurrent work that are evaluating quite different mathematical functions from the non-bonded interactions. We can actually get them running on the GPUs also, because the GROMACS developers have done the code work to do this. In fact, this was actually code contributed by NVIDIA themselves, because they want GROMACS to run well on their GPUs. And so these can be evaluated on either the CPU or the GPU. So the two different kind of workflows we might have now. If we just added bonded interactions to our previous simulation, then we would still have the same interaction, same need to compute pairs, then bonded forces, then the short range, and so forth. However, if we offload the short range to the GPU, then we will see that we need to send the positions to the GPU, run the short range, and then receive them back. Then we need to combine them all. So that's a separate phase that needs to happen. And then when the pair list has not yet expired, we can loop as usual. When it is, however, expired, we need to go to the pair search list again. So in this kind of workflow, we've just got the short range non-bondeds running on the GPU, which is smart because that's the most computationally demanding. So that the GPU, which typically has more total computer power than the CPU, can do the biggest unit of work. If, however, it's relatively strong compared to the CPU, it makes sense to push even more work there. So in such a case, we might move the bonded forces also. So rather than have them running on the CPU, we now run them on the GPU as well, and everything else stays much the same. Now the need to combine all the forces is a bit lower because everything was done on the GPU, so it might have been done there already. So there's ways that we can express to GROMACS that we would like to run either of these kinds of modes. So using GMXMD run, which is the typical command line one might be using, there are some command line options. We can say that the non-bonded component with -NB runs on either the GPU or the CPU. Likewise, the bonded component can be directed to run either on the CPU or the GPU. So the difference between these two run configurations can be expressed by whether you run with -bonded GPU or -bonded CPU. There is a default. That default changes a bit according to what hardware is detected and what simulation type is running. So exactly what the default is not important. If you're just doing the normal thing of running and not worrying about your performance because you're not running enough of this type, then you'll get what you get. If you want to make sure you're getting the best performance, then you want to think about trying both of those options. So here's another quiz. When would it be most likely to benefit from moving bonded interactions to the GPU? Have a think about those few options, and then I will talk about the solution in a few seconds. So when there's two tasks running on the GPU, there's more coordination overhead that has to happen there, and that offsets some of the benefit from speeding up the bonded work. If the CPU is powerful enough to finish the bonded work before the GPU finishes the short-range work, then exploiting the CPU-GPU parallelism is best. What we're saying here is if the CPU is powerful enough that the bonded forces don't take very long, then the CPU will be ready to take the GPU forces whenever they get ready. If, however, the CPU is extremely weak, then the bonded forces might still be running when the GPU is already done, and then the GPU spends its time waiting for the CPU to get finished so that it can send its forces back. In that kind of scenario, where the CPU is really weak, we would have done better to have more work running on the GPU, so put the bonded forces there as well. So how do I understand what is relatively weak and relatively strong? That's a tricky one. In the abstract, there's not even a good way for the developers to query the hardware and understand this, because it depends how things are working at runtime. However, you can just run the two options and see which one runs faster, and that's enough for working in practice. So that's what we're going to do now with an interactive exercise. We're going to download a run input file that is able to run in these two modes, and we'll use it to experiment with the task assignment. There will also be a job submission script that we need to edit. There's a couple of lines marked fix me, so you need to remove the fix me and then try to achieve the goal stated in the comment before that line. If you're not sure what to do, have a look back over the material we just talked about. There's clues there to guide you to the right answer. Oops, sorry about these mentions of PuTTY. That's the last cluster I developed this course for. I will fix that before I do it again, but it should say Navigator there. If you're not running on Navigator, you'll need to perhaps make further changes to this file. Maybe you won't be able to do that in the time we have available for this workshop. But do check your documentation and work through it at your leisure later. So I'm going to switch now to my terminal. If you have followed these instructions, then you'll be able to get access to these files in that way. I'm going to follow them myself right now. Copy that. And go to copy that to my terminal. I'm going to go unzip exercises. Oh, that's surprising. Why there's no content there? I'm not sure why that is. I will get the content directly from the page. Sorry about that. It's whether I constructed a zip file wrong. So I'm going to copy the link address there to get the input file. So I've downloaded the exercises for this first one. So we don't need to worry about what's in the TPR file. This is a special input file that contains all the information GROMACS needs to run a simulation. When you're getting started using GROMACS, it's often quite difficult describing your simulation systems so that GROMACS's tool GROM can build this TPR for you. But for this workshop, we'll treat it as a black box. Let's have a look at the script. So because I wasn't aware of the reservation, we'll need to edit that so we get access. You can see here I've asked for 1 GPU, 20 cores associated with it. This is using the version of GROMACS that I built. Let's keep it simple and keep using that. You're most welcome to use the one that has been provided for you with a module on Navigator. So here are some options that are important when you're comparing performance. And down here we see the activity. When we run this script, we're going to run GROMACS in its default mode just to see what the performance is. And then we're going to run it in 2 different modes explicitly, because one of those probably corresponds to the default, and we can compare the performance and see that it's the same. But otherwise, we want to see what the alternative is, whether that's worthwhile. So, in order to find out what I might want to do, I look back here and say, okay, I want to run in these 2 different modes. Here are the kinds of commands I want to run.
Mark, can I jump in for a second? So we've got a question in the live doc saying someone is having trouble or believes that Veracruz projects, whatever the link is empty. I don't have access to this system, so.
Yeah, I just discovered that myself. I won't try to fix it now. Please do copy from the download links you have available in the exercise. It would have been easy to miss that, but you can download those. That'll come to your local machine, unfortunately, but if you, for example, right click on that, you can copy the link address and use that to download to Navigator. So commands like wget and then pasting in that kind of link will get you access to the files. I'm sorry about that. I made those.
Thanks, Mark.
Okay, and if you have any trouble doing that, then please do follow along what I'm doing, and you'll get most of the value from seeing what I'm doing. I don't think there's anything else that's good. Let's try. No, there's nothing else there. Okay. So I'm now going to complete the exercise here by filling in these fixings. So I want to run the non-bonded on the GPU and the bonded on the GPU. So use both those slides like that. Here I want only the non-bonded. Okay, so that looks good. And then the script will let us know when it's done. So let's run that. May be able to fix that zip file for you in the background while I wait. Okay, those of you working on Navigator, the zip file now has the full contents. So if you want to go use them, please try copying the zip file again and unpacking it. You should have the right contents. In the meantime, let's see if the job is still running. So I'll use the slurm command SQ, which says slurm show me the queue. And I'll filter on my username so that I see when my job's still running. It's not. Hopefully that means it's finished. Let's have a look. Yeah, it's run something. You can see here that it did select the GPU to run. It's running the particle or non-bonded work there. And I moved on and did some more. And it finally said done. Okay, so we know everything's finished. We can see also that there are 3 log files written. So that's good. We were able to compare the performance there. Let's go back to the instructions. While I was running, I could have been using tail -F to watch the output. I didn't do that, sorry. That would have let me know immediately what was done. However, we can now look at these log files using the same tail command, slightly differently. You use tail style log to see the last chunk of each log file. So I could type that in manually, or I'll just paste it as I did then. What this will show is the last 10 lines of each of these 3 log files. Here's the first one we did, where I just let GROMACS run in its default. And for this particular kind of simulation, we got 535 nanoseconds per day. There's other data being shown here. 16 seconds, for example. Most of the rest you don't need to worry about. So we got quite reasonable performance. This is a very small system, so that's a relatively high number for performance of MD simulations. You might see lower numbers typically. If we ran it with just the non-bonded offload, we get only 503 nanoseconds per day. So that's a bit worse. We'd like to do more simulated nanoseconds per day so that you get more sampling of your simulation system so that your scientific quality goes up. If, however, we only send the non-bonded to the GPU, then we get back to 531. So probably the default implementation is the same as non-bonded only being offloaded, because those are the closest in performance. There is naturally going to be some variation. We are doing 10,000 steps in these times, so there's time for some variation to be smoothed out, but things do change. The computers are shared resources, and there are a bunch of things that don't always work exactly the same way. If you would run this for hours, then you would see these comparisons be much more reliable, but we only did a few seconds worth of runs, so not terribly reliable. So what we learned here is that the default implementation is just offloading the non-bonded, and we've been able to learn that we could offload the bonded if we wanted to, but it would make our simulation run slower, so that's not a good idea in this case. Your mileage might vary. If you're on a cluster with a relatively strong GPU and a relatively weak CPU, then you might see this trend reversed. I wasn't surprised to see this particular trend on Navigator because the CPUs are pretty fast-moving, so they're very good. So from this lesson, we learned that we can do concurrent calculations computed in parallel. GROMACS handles buffering the short range interactions automatically for you, and the default is often quite a good way to run GROMACS. Are there any questions on that exercise or that content? Now would be a good time to look through those before we move on to more complex ways of running GROMACS with GPUs. If not, I will move on to the next topic. So PME is the implementation of the particle mesh EWALD method in GROMACS. It is the dominant way of doing these kinds of biomolecular simulations in GROMACS and indeed other MD packages, because even though it is more expensive than not treating the long-range component of the electrostatics, it gives you much more accuracy in your simulation. It turns out to be what. It does make the simulation rather more expensive, as I said, so that's not a good thing. However, what it does do is give us some more units of concurrent work that can be scheduled differently. So there are several features within GROMACS that allows us to move this concurrent work around. We'll only talk about some of them today. To be aware that there are others you can move the PME work to different nodes entirely if you want to. By way of background on the PME algorithm, most similar systems of interest have inhomogeneous distributions of partially charged particles. So the analogy I talked about earlier of forces cancelling with water molecules on either side of a relevant particle isn't true for interesting systems in practice. You don't always have the same kind of molecule at the same distance, so you don't have as good cancellation as you might have if it was homogeneous. And it turns out simply neglecting those interactions is not accurate enough. You can't just make the cutoffs big. That reduces the size but doesn't eliminate them. Instead, pretty much everybody these days turns to some form of the EWALD method, of which GROMACS has implemented efficiently the particle mesh EWALD method, where the shape of the short range interaction is modified. A compensating fix is made by doing extra work in a concurrent long range component. In the unmodified column interaction, we have this blue curve where we have a 1 on R shape, well, actually, this is a minus 1 on R squared shape because we're looking at the forces rather than the potential. So we've taken the derivative of 1 on R to get minus 1 on R squared. And we would, in a typical simulation, compute forces for all particles at these distances up to some cutoff here, 1 nanometer. You can see here that even if we're a little way past 1 nanometer, we still have significantly large forces, and this is the origin of the artifact we're trying to get rid of. In PME, what we do is subtract off a Gaussian-like curve, which we can see here in green. Subtract that off the blue curve to get the red curve, which has approached zero forces much more quickly. So we're much happier doing this truncation. And then we have to add that component back in what is called Fourier space. It turns out to be computationally efficient to do this on a three-dimensional grid that we can treat with a fast Fourier transform, which is a very commonly used computational chemistry or computational science technique for treating regular grid-like problems. There are very good implementations out there, and GROMACS is able to take advantage of them. So what this does is mean that we have a modified form of our short range work and another piece of work, and that other piece of work can be done concurrently. Sorry, is concurrent, so can be run in parallel. That concurrent work can be done on either the CPU or the GPU. When we're on NVIDIA GPU, we use the cuffed library. On the CPU, sometimes FFTW, which we saw earlier. They are very good for that. One of the most useful attributes of this PME algorithm is that the share of the computational work of the two components can vary. We can scale the short-range cutoff and the 3D FFT grid spacing by the same factor to give a model that is just as accurate an approximation. This relies on the fact that we can choose how wide this Gaussian is underlying this green Fourier space component in a way that trades the amount of computational work at constant accuracy between these two concurrent components. So this PME tuning is on by default. It works extremely well. You don't have to turn it on because it's on by default, but if you would say minus tune PME, you can turn it on explicitly. If you want to force it to turn off, do that. It's very rare that you would want to do that. So in practice, MDRun spends the first few thousand steps doing an inefficient simulation while it tries out some alternatives and then uses the optimal result for the rest. All right, let's do it. So we have a quiz now. If MDRun has to compute the van der Waals interactions between particles, should the cutoff for those be changed to match the tuned electrostatic cutoff? So we haven't talked about this yet, so I'm just throwing out a factor that might be relevant if you have a simulation that has both Lerntrans and van der Waals. Some of you won't know the answer to this question, that's okay. Have a go and then look at the solution. Even though it might seem on the surface like you want the cutoff to be all the same so that everything is better, and indeed a bigger cutoff would be more accurate, that is true. However, the force field was parameterized using such cutoffs, and so the errors that are introduced by the truncation artifacts have been built into all the other parameters that are going on. So they're compensating for each other. Even making it longer, which is a more accurate approximation to what you really wanted to have in the first place, can wreck that balance. So in the PME tuning, MDRun preserves the cutoff of the van der Waals to the same length. This means PME won't tune to very short lengths, because that would mean that the pair list can't be reused for both van der Waals and electrostatics. Typically, however, that's not important for performance, but you might see that MDRun produces output that says I couldn't try short distances, and this is why. So when PME is involved in the MD workflow, if we still have our short range component, which now has a different functional form being offloaded, we now have a new chunk here in green, which is the long range unbonded forces. So they too are being computed on the CPU by default, along with the bonded forces and maybe other stuff like forces resulting from AWH. So this kind of run configuration can be set up by using this kind of command, where we've added to the fact that the short range is on the GPU and the bond is on the CPU. We're saying that the PME is also running on the CPU. So here's another quiz question. When would we most likely to benefit from moving PME to the GPU? Do we want a strong CPU or a strong GPU for that choice? Hopefully that was a straightforward one to think about. Again, running two tasks on the GPU adds more overhead there as well as more work, and that can offset any benefit from speeding up the total work. So if the CPU is powerful enough to finish all its work, then leaving PME on the CPU is best. This is the same kind of challenge we were looking at recently with the bonded forces to the GPU. More kinds of work, more overhead, more complexity. If we did do it, however, the run would look like this. Now the green component is running on the GPU rather than on the CPU. And we combine some forces there and send them back. before we combine all the forces in the CPU for the rest of the updating phase. This particular configuration can be selected by making sure that you have minus PME GPU. Turns out that the second half of the PME task is harder to make run fast on the GPU than the first part, particularly when there's a short range task also running on the same GPU. So GROMACS actually permits the PME task to be separated so that that second part can run on the CPU instead. If we run it in this mode, we get a little more complexity in our workflow plot. We do the first part of PME, so-called charge spreading on the GPU, send the data back to the CPU, and now we can do the rest of the PME workflow on the CPU. This too might be the best choice for your hardware, depending on the relative strength of your CPU or GPU. So if you have an extremely weak CPU, you want to do it this way with everything in PME offloaded. If you have an extremely strong GPU, that's when you have an extremely strong GPU relative to your CPU. If it's only moderate compared to each other, then you might find that this works best. That too depends on how much bonded workload you have and whether you have other forces being computed as well. So things like the pull code used by AWH or F3G perturbation methods mean that this purple unit of work is quite large, so you may not want PME in hybrid mode if you're doing those other things. To get this mode, you say PME on GPU and also minus PME FFT CPU. So we come to our next practical exercise. If you struggled with the zip file earlier being empty, please have another go because I've filled it with content now. So you should be able to copy the zip file again and then unpack it and put stuff there. And then you'll be able to follow these instructions to transfer into the directory. So I can do that also. There we go, everything inflated, there's good content there. So let's go into exercises using PME. There's two different shell scripts here. We'll look at script.sh first. This is a different TPL file than we used earlier. The previous one wasn't using PME. This one is. I need to edit this to use the reservation that we have. Using the version of GROMACS that I have just for simplicity. And so here we have the work we're trying to get done as the exercise in these comments in blue. We want to run MB run assigning only the non-bonded interactions to the GPU, and PME to the CPU. Yeah. So please do follow on with this exercise yourself. You can practice typing these in and understanding how things work and being comfortable. So here we have MD run assigning the non-bonded interactions and all of the PME tasks to the GPU. So MB GPU and PME GPU. And this last one is all non-bonded to the GPU. And some of the PME to the GPU, but not all the GPU. Great. So now I can run that. So now I can use tab minus F to follow along the progress of the job. So we see here that, in fact, PME is also now running on GPU 0. We can see here that the runtime report is confirmed. What we might have known was the default, but we didn't. We haven't talked about it yet. The default is, in fact, that the PME tasks will do all aspects of the GPU. So we should expect that the default performance is the same as the one where we sent all of PME to the GPU. So this will take a couple of minutes. check whether there's. It's taking relatively long. So let's finish the first job and let's start the next one. It's on the third job now. And finally the last one. Can be fun when running GROMACS to see these quotes that come up from time to time. Here's a quote from John von Neumann, who's one of the early researchers in computational science. Anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. Which is somewhat amusing. It's very hard to produce true random numbers on a computer that's been built to be deterministic. Turns out there are some funky methods in hardware one can use to get actual physical randomness, which GROMACS will use on the few occasions it needs random numbers if you have it available. So I'm still waiting on this last one to finish. Apologies for the baby crying in the background. It's his nap time. Doesn't always like his nap to start. So we see here that by default, this simulation got 96.5 milliseconds per day. With all of the non-bonded short range and long range and all components of the PME running on the GPU, we also got about 96. This was probably the default. If we only put the first component of PME running on the GPU, then it was much slower, only 71. So we deduce in the situation that the GPUs are strong enough that doing all of the work there is more efficient than trying to use some of the CPU. So that's a good thing to have learned. Indeed, if we don't put any of the PME work there at all, we get a significantly slower simulation. So GPUs here are very capable for this work, even though the CPUs are very strong. The GPUs are more capable for this kind of workload. And so we see that getting the offload is working quite well for us. So let's come back to here and check that I've thought about these things. So let's have a look at the highest performing one, so that we understand the kinds of things we see. So here's the one where we offloaded all of the PME components to the GPU. So here we have the version reports. And there's a little bit of hardware detection result here as well. We see that there was one GPU found. Details about the hardware. And there's a report of your user input, which we can go over, and then we see here that GROMACS has acknowledged that there's one GPU selected. There's two tasks available for it, the short range PP work and the long range PME work. The various tasks will be distributed with the CPU and the GPU in the way that we expected for this particular job. We send all of the PME tasks to the GPU, and GROMACS is confirming that's what's going to happen. And so here we see the output from the PME tuning, where GROMACS started with particular choices for the PME grid and the coil cutoff, and then tried various alternatives and observed how much work got done in how long the particular numbers of steps took in terms of CPU cycles, and decided what is best. And in fact, that's where the most work is pushed to the PME component. So that seems to work best on this GPU. And then once it's finished the tuning, now it goes back to running with that tuning. Here's where we actually measure our performance report, which comes here at the end of the log file. This is what we were able to see earlier using there. Okay, so we've looked at those sort of thoughts there. So there's the working solution that you can see for this exercise, and there's sample output there. So I computed this yesterday, so don't be worried if you haven't been able to follow along effectively during the exercise now. You can have a look at the log files yourself and observe the same sorts of trends. The actual numbers are different because the machine is different today, but the general trends are as expected. Putting all of the PME work onto the GPU is still observed correctly. So there's one further piece of work that can be moved to the GPU. A couple of years ago, the GROMACS developers completed the job and said, okay, we've finished being able to export the dominant parts of the computational work, forces, to the GPU. However, we're still having a bunch of overhead from having to move the positions to the GPU to compute the forces and having to move the forces back so that we can then do the updating constraints on the GPU. What if we just did everything on the GPU? Then we wouldn't need to do much moving stuff around. The outcome from that is what we see here in this next workflow diagram. We still have to do our pair search on the CPU because we haven't followed that to the GPU yet. We send the pair list there and it stores it for a while. When we get the position coordinates, send them necessary, because we might have some other work to do here. For example, if there's bonded forces that haven't been offloaded, or if we're doing AWH, there's work to do here. So the position coordinates come back from the GPU at this point. If there have been these other forces, then they get sent and coordinated there. But if we have the short range and the bonded and the ping all running on the GPU, and none of these other forces, then there isn't any need for this communication phase. And so that's the case for the vast majority of GROMACS users simulations. They've just got these three natural components, so it's very convenient for them to be run. If you're running AWH, however, you have other forces, so there will be a little bit of inefficiency here. Fortunately, that workload is not large, so by the time the GPU does all of that work, AWH will typically have done its work, and will already be ready and waiting for the GPU. So it shouldn't be a big deal. Then all those forces can be combined and we do the upgraded constraints running in the GPU. And again, we check whether the pair list has been expired. If it has, then we build it again. Otherwise, no, we just stay on the GPU. So in the typical case where we don't have other forces, all of this loop stays on the GPU. There is no time wasted transferring data back to the CPU. So we should expect that this will have savings from not needing to do that transfer, and also probably some savings from actually being able to run this faster because we're applying more hardware to the problem. Turns out the GROMACS developers have done a good job at this point, and we shall see how good a job they did by having a look at what results we get when we run the GROMACS simulations with the update also on the GPU. It is true that not all combinations of algorithms are supported, but when they are, the benefit of running the updated GPU is extremely useful. So we can do this in the same folder we're just doing the previous exercise. The same TPR is useful, but we will change the submission script so we look at different aspects. So now we can look at the on script. Edit, so we use the reservation. And non-bundle on the GPU, me on the GPU, update on the GPU. So what I haven't done here is move the bonded work over. Sometimes it's a good idea to move the bonded, sometimes it isn't. That's cool. Yep. It turns out that the bonded workload is quite messy. That's very difficult. Very efficiently on the GPU. So if you have a strong CPU, you might expect that it's good not to send the bonded over. Unfortunately, the auto tuning capabilities of GROMACS are not advanced enough yet to work out whether to do this. If we send absolutely everything to the GPU, then we'll see the performance there. Great. Let's get that sent off. So we'll look at the second one of these. So we now see in the summary report that yes, the update and constraint work will now run on the GPU.
Perhaps it would be useful to narrate instead of just typing it in the document.
Yeah, I'll talk about them later.
Okay.
Just being efficient while I'm waiting for the job to run.
Sure. Mark, you're muted.
The jobs are finished, so we can have a look at our performance. We can look at two different runs we just did now. We can compare the performance. So when we just had non-bonded PME in the update running, now got 135 nanoseconds today. When we added the bond as well, it got a little bit slower. So what we're seeing here is that for the very messy workload that is the bonded, it's still worth putting them on the CPU in this case, because the CPU is also pretty capable. That would change if you were running this on, say, a laptop, then probably you want all of it to run on the CPU because all of them to run on the GPU, because the CPUs in the laptops are so relatively weak. Mileage will vary, depends what you're running on. If we look at all of the log files now, we see that actually let's just grab the lines we care about. I want to reduce that complexity. We see that when we aren't running the update on the GPU, we get between 45 and 96 nanoseconds per day, which is nice, but not as good as when we started running the update on the GPU. Now we're getting 128 or 135 nanoseconds per day. So as expected, the avoidance of needing to transfer data back to the CPU has given us a substantial benefit, and we probably also did spend less time computing the updates and constraints phases as well. So it's worth trying whether you can get the update running on the GPU. For the moment, in released versions of GROMACS, you'll only be able to get that available if you're running on a single GPU. We're working on parallelizing that, but it's a bit difficult. To test all of the possibilities as well. So it is coming, but for now, if you're running with only one GPU, then getting the update running on the GPU is quite valuable. And that might be more valuable to you than trying to organize anything else. So we have one more short lesson before we finish. And that is thinking about how to design an efficient simulation. There are multiple things you should think about whether or not you're running on GPUs. You want to choose a simulation cell with just the right shape. You want it to be large enough for the science and the physical model, but no larger because you don't get any advantage from doing the extra computational work. It just slows things down. Make sure you're using constraints, and preferably hydrogen bonds constraints. They allow you to take a larger time step for no significant degradation in quality of all of your observables, and in practice, the observables that most people are interested in don't degrade at all. So you will get the extra throughput value. Make sure you're using the typical water models the way they were designed, as rigid, not flexible. Make sure you're using the fast 3-sub water models unless you've got clear scientific evidence that something else does a better job for you. With hundreds of different water model variations out there. Some people spent their whole research career making new ones. However, it's very unclear whether any of them are good. Once you put a solvent in the system, once you put a solute in the system, all of these water models have been shown, oh yes, this is 2% better for a pure water simulation. But that doesn't necessarily translate to there being a solute in practice. So stick with the tried and true there. If you've got layers, then make sure you align them in a way that works well, because if we're using multiple ranks in the simulation, which we haven't talked about today, there's good and bad ways that will be handled automatically. If you've got a simulation cell that's approximately spherical or cubic, then that's fine. However, if you've got one dimension that's very much different from the others, then you want to choose the short ones to be X and Y for the same reason. It's very tempting when you start out running a simulation to say, oh, I'd love lots of output. I should write my energy out every step, and I want my forces all written out as well. All of that costs a lot of time. We can't run the simulation on the GPU if we're constantly having to transfer everything back to the CPU to write the output. So that'll take a lot of time, and it's not even organized to run in parallel at the moment. The GPU stops while writing output. And the reason for that is it doesn't make much sense to write output very often. Nothing changes in a couple of femtoseconds, so you don't want most of this output every step. Maybe you want every 100 steps or 1,000 steps. At that point, there's very little loss. So that's why we haven't bothered to parallelize that work yet. So yeah, write the output you know you will use. If you don't know what output you're going to use, stop and think before running your simulation. If you don't know what output you're going to use before you run your simulation, maybe the actual answer is, I don't want to run a simulation because there's no output I can get from it that I will be able to use. Don't just run a simulation for the joy of running on some big computer. You want to do science with it. There's a few other tips there. Can write energy output groups. Some people think those are useful for some kinds of analyses. Personally, I think they're basically useless because the force fields were not parameterized to produce sensible groupwise energies. If you do want that, do it later with GMX71 rerun. Don't slow down your production simulation. Much more efficient to do it in post-processing. You don't want temperature and pressure coupling every step. That also slows things down because those bits of code run on the CPU. So losing value from the GPU by writing them very often, it doesn't give you advantages anyway. Make sure that all the different NST parameters that determine how frequently things happen have some large common factor. It's tempting to say, oh, I want output every 3 steps and I want this other output every 7 steps, but then the way the implementation is done, everything has to get done every step because that's the largest common factor, 1. So give everything a large common factor like 10 or 100. So, oh, there's a duplicate there, each one constraints. That's already talked about. Another thing you should think about is whether you need speed or throughput. Sometimes you need one trajectory to run as fast as possible. And that's mostly what we talked about today. But often your scientific goals are best met by running several similar trajectories. You can set these up in GROMACS so that they're statistically independent because they've got different starting velocities that will diverge very quickly from each other. But if you actually want aggregate sampling across multiple trajectories, then running multiple simulations is very good. That actually works well in parallel because those trajectories themselves are concurrent. When you're running a single trajectory, the GPU is idle when the update and constraints aren't running on the GPU. However, if there's 2 trajectories running, sharing the same GPU, then they'll settle on the pattern of running mutually out of phase. When one trajectory is doing the update on the CPU, the other is computing the forces on the GPU. It can look a little bit like this. But 2 simulations running sharing a common GPU, then things will settle. Right. If we tried to start work while the GPU is busy doing other stuff, the work will just wait. And then it'll start later. Then gradually everything will settle down into this simulation uses the GPU, and while it's doing the update, the other simulation uses the GPU. You can set this up manually yourself if you really want to. You would need to do that if you want 2 very different kinds of simulations running together. But there's capabilities built into GROMACS to do this automatically. This is the same capability that's used for things like multiple AWH replicas and replica exchange algorithms. So it works very reliably. So you get really good value from leaving the update on the CPU in these cases so that the GPU is free to do work for another simulation. The sweet spot is, unfortunately, 2 simulations. If you've got more than 2, then you don't have enough concurrency for this to be worthwhile. But it's a valuable technique if you know you can take advantage of running multiple simulations. So to get something like that run, you want to use the MPI version of MD Run, which we haven't used yet today, and you want to set up multiple simulations in multiple directories. So if you had 2 GPUs, like the nodes that exist on Navigator, and you had 4 simulations in directories A, B, C, and D, then you can set it up to run very efficiently like this. There's a lot more background information available in some of these papers here. Again, things working well. They have been updated over time as GROMACS's capabilities have changed and the strengths of the GPU have been changed. So do take advantage of that sort of background reading. That's there. So I think that's the end of our material here. Yes, it is. So if there's general questions on that material, I'll take that first. And there's a couple of questions about things not directly on the workshop topic that I'll talk about. First, anything you've heard about today that's confusing, please do either type in the chat or ask in the document.
Thank you very much, Mark. I think it was very interesting. I've seen that some of the questions already been answered in the live document. I have just a question from a manager, or let's say, for taking into account possible future investments in hardware. Do you think that the simulation in GROMACS could benefit to have more GPUs in one node? We just have 2, but you know, for artificial intelligence and workflows, normally people prefer to have more GPUs in one node. I don't know whether GROMACS presently or in the future will take advantage of that.
It absolutely can. I did observe earlier that the GPU update is only on by default in the single GPU case. Absolutely, you can run an individual GROMACS simulation across multiple GPUs. It's not as efficient as trying to run multiple simulations each on a single GPU or multi-simulation GPU sharing I talked about. But if you're wanting to run one simulation super fast, then absolutely GROMACS will run on multiple GPUs. We are seeing that trend already. There are plenty of clusters in Europe now and coming that have 4 GPUs per node. I haven't talked about these capabilities now, but it's certainly possible to run a simulation using GROMACS where 3 of those GPUs each do part of the short-range work, and one of the GPUs does all of the PME work, and then all of those updates get done on the 3 MPI ranks that are handling the short-range work. So NVIDIA has been working with us for a couple of years to try and improve the situation, so we can also do the update work on the GPUs. Those capabilities do exist already, but they're behind some developer features with some warnings that we haven't finished testing this on enough stuff yet. So absolutely, from a cluster management point of view, keep buying nodes that have more and more GPUs. GROMACS will work well on them. The released versions of GROMACS now haven't completely built out those capabilities. I hope that we'll get enough testing done this year that we'll be able to turn those features on for users.
Okay, thank you very much. In the future, I believe you can share your link, right, from the National Competence Center. It would be very useful. So we'll be there for a while, I guess. So this one, because you have all this material there, so it will be very useful. Thank you.
Okay, we have a couple of questions. I'll start from the bottom just because they're simpler. I'll share that page. Is the GPU able to use multiple GPUs linked together? Yes, however, SLI is a thing that's only relevant for gaming. You physically can't run computation jobs using it. Only the gaming APIs support it. HPC GPUs do that in other kinds of way. Support for that is used in GROMACS. I forgot to find detail of whether any of that's able to be used in released versions yet. But NVIDIA has been working hard with the core team to get those exposed. Hopefully we get those tested enough this year that we can make them available. That will make a dramatic improvement in performance, which of course is what NVIDIA wants, because they are able to build these very dense nodes with lots of GPUs. Somebody asked, how can you change the precision of GROMACS? If you want to, then the CMake option, GMX double, can be turned on. It's off by default, and almost everybody wants it off by default. Your cluster admins will be very happy to install a double precision version alongside the one as well. You might find that if it exists, it will be called GMX_B, which is the default suffix for it being double precision. So here are some of the environment variables that can be set to get a lot more use of multiple GPUs more efficiently running in GROMACS. I can't really talk about these more now because they're not officially available features. You have to run these with multiple MPI ranks. That can be on multiple GPUs, tends not to be worthwhile. But yeah, these are things that we are testing, but we need to run them on a wide variety of hardware and simulations before we would trust them enough to put them in the hands of users who are spending significant science on. Somebody else had a question about, oh, I added a ligand into my system. I don't think I changed anything else, but I saw a big drop. So I was getting 280 nanoseconds a day and then it dropped to 190. Adding 160 more atoms into a system of typically 10 to hundreds of thousands of atoms wouldn't change the performance much. A couple of nanoseconds per day, perhaps. So our guess from Joe and I assume you're answering the questions, that's Alessandro also, was that in fact something else was changing, such as the simulation box or the flags. And in fact, yes. So yeah, apparently you were changing something there. So yes, that's going to have a direct effect. So good, glad we're able to get that addressed. Are there any other questions before we bring this session to a close? I understand there's a break scheduled next. Happy to take them orally as well, if that suits you better. No, then I guess we can bring this session to a close. Thank you all for your willingness to come here and learn about GROMACS. I hope you have a good experience using it in the future for your science. Please do remember to get in touch with developers if you have questions. There's a great forum that I'm sure Alessandra has also mentioned in the past, gromacs.bioxl.eu. There's lots of questions been asked already there. Do search it as well, because often the questions you've asked have already been answered.
Okay.
I think I'll pass back to Pedro. Thank you all for a good workshop.
Well, thank you all. Thank you from our part as well. Thank you very much. Yeah, so I think we'll get into the break right now, right? And we can, yeah, but please.
Can we come back in
weight histogram method? Sorry. Yeah, so hopefully everyone can see my screen and the text is big enough to read. All right, good. Okay, so we'll actually start by just directing people. Hopefully someone can post this link into the chat or into the live document just to make sure that everyone is on the same page. But this will tell you how to get started with the tutorial.
Joe, sorry, could you a little zoom out? So, because now we see a lot of white in the...
Oh, you mean zoom in?
Zoom in, sorry.
Yeah, it's a difference between the resolution of my monitor at home and my monitor at work.
Okay, that is good. Okay.
Yeah. All right. So yes. So there's basically two ways to run the tutorial. If you've configured everything ahead of time, you can run it locally. So I can't really say anything about for Mac or Windows users. For Linux users, the steps listed more or less work. If it's the first time you've ever used Conda, it'll prompt you to make one alteration to your bash or C file. And you'll also actually need to run Jupyter Notebook tutorial, not AWH tutorial. Renaming also won't work because of the internal links. But if you just run it with the free interactive binder, it will just work. So this is what we recommend for following along at home here, unless you really want to run it locally. So I'll give a moment for everyone to get binder started up. It may take a while. This could make it a little easier for people to follow along at home. But in the meantime, perhaps I can start going through a little bit. So we need to execute the cells. So we should already know by now, since we've done another tutorial, but the way you execute a cell in a Jupyter Notebook is by clicking on the cell anywhere and hitting Shift Enter, and then it'll execute that cell. So the first cell is just making sure that the notebook hasn't been modified. It's telling me mine has, which in this case, I think just means that it's been saved, because you can actually see that this is the first command that I have run. So any modifications cannot have been from running actual commands. But that's fine. All right, so today we're going to learn how to calculate a probability of mean force with the accelerated weight histogram in GROMACS. And so, you know, Beric gave a nice talk about this yesterday to give some background to the method. And so, you know, what are the inputs you need? Well, the main thing you need is actually a reaction coordinate that you can use to drive the system along, because you want to sample along some reaction coordinate and, you know, learn the free energy landscape. So there are some other kinds of free energy calculation methods that can help you learn the reaction coordinate if you don't know it. For the AWH method, you have to give the reaction coordinate as an input. Okay, so here I'll actually run the binder. No, maybe I won't run the binder. At any rate, I spent about 45 minutes trying to get NGL Viewer to work. It has not worked, so I'm not even going to try to run this cell, but you should be able to run it at home and get, you know, if you're using, oh, here we go, now this is working. So I've tested to make sure that it works in the notebook. So why don't we just go there? Oh, and in the notebook, it also renders this nice picture. So today we're going to calculate a PMF, which again is just a potential of mean force for the opening of a DNA-based pair. So this is a very stable structure. In order to open this, it requires breaking some hydrogen bonds. As Beric mentioned yesterday, the energy difference means that it is 1,000-fold less likely to see the system visit an open state than to see the system in a closed state. So this is why we need to use some kind of enhanced sampling method, because otherwise we would have to wait for a long time to see anything to happen. So if I run the first thing here, we should be pretty confident that it can't change, because that's the whole point of my binder. So now if I run this, it'll actually hopefully give me an NGL view window. So just to say something here, I mean, so VMD is really powerful for certain kinds of simulation visualization, but if you just want a quick and dirty look, and especially if you're using, you know, an IPython notebook for visualization, you know, NGL view is great. You know, you have to do a little bit of preliminary legwork ahead of time, you know, if you want to look at trajectories, things of this nature. Looks like it's still not coming up. So hopefully it's working for people at home, but maybe it's just slow because there's a large number of people.
It's just slow. It will appear.
Okay.
It's working on my binder. Yeah. So
yes, yeah, I tested it a few days ago to make sure that it was working on my binder. So it should work eventually. But at any rate, if it were working, it would show a DNA helix looking like the one in this image here, but with 2 nitrogen atoms highlighted in green. And so the distance between these 2 nitrogen atoms is going to be our reaction coordinate. So if you're following along at home, you could actually use VMD. And so this cell would actually launch VMD, not in your browser, but externally. And then you could look at it there. We won't do that here. You can't do it if you're using the MyBinder. Yeah, it looks like it's not gonna come for me. Nope. Okay, well. At any rate, it should be possible to look at. It's unfortunate that we can't get a representation. But all right, so let's move along, assuming that we've already looked, at the 2 nitrogen atoms that we're using as our reaction coordinate. So for the purposes of this tutorial, we want to focus on AWH and not on some of the sort of basic steps that we worked on in the tutorial yesterday, such as minimization and equilibration. So we'll just assume that we have already built an equilibrated system, and so that we're almost ready to go. So for AWH, we're going to need to add some extra parameters. So, we'll CD into the directory that has the data and also list the files. So for those of you not familiar with Bash, CD is change directory and ls is list. And -L is just giving you a more verbose output, basically. All right, and so just like in the question we had about the performance with ligands, a good way to understand differences in simulation setup is to look at the MDP files. So you can use diff for this. And so here, the arrow pointing to the left is going to be the first file that you give as an argument to diff, and the arrow pointing to the right is going to be the second file that you give as an argument to diff. So what are the differences? So we're going to give it a different title. One is equilibration and one is an AWH simulation. We're going to have more steps in the AWH simulation because we need to make sure we have sufficient sampling. And then we're going to have to turn on a bunch of options related to AWH. So you can actually read in more detail about these options at the GROMACS manual page, which is extremely useful. So there's a bunch of options, and some of the options have more than one thing that you can pick. And there's a staggering number, perhaps you could say, of options. So I'm not intending for you to try to read the stuff I'm scrolling through, obviously. I just want to give a demonstration of how long the potential number of parameters that can be defined as a simulation are. So we recognize that this is one of the, still hasn't rendered. We recognize that this is one of the more complicated aspects of the simulation, is picking your MDP files. And that's why we have tutorials like this, to try to give some best practices. So in this case, we're going to use pull groups as the reaction coordinates. And we're going to have 2 pull groups. And we're going to update we're going to write output at some frequency, 5,000, every 5,000 steps. We're going to have some, so we'll actually go through all this. So I don't need to read through all this now. All right, so the MDP file depends on some definition of atom groups, which we're calling base in 1 or in 3, and partner in 1 or in 3. And we need to make an index file, which is something we talked about a few times, to give as an input to GROMPP. And so the best way to do this is using GROMACS select, which is something that we also talked about a couple of times yesterday. But we won't go through this because we're focusing here again on AWH. So we've just provided the index file for you. So if we run that cell, we see that base in1 or in3 is index 338, and base or partner in1 or in3 is index 936. So since we're expecting to have the reaction coordinate be the distance between two nitrogen atoms, this looks right. But what you would want to do, if you were not doing this tutorial, which, hopefully we've done a good job of validating, but instead, doing your own research project, is you'd want to go in and visualize and make sure, for instance, in VMD, that the indices correspond to the atoms you expect them to. So we're not going to run the simulation. We're just going to use data that's been provided, but just for practice, we'll show what it looks like to run GROMPP, which is how you generate your inputs for GROMACS MD run. So again, a nice tip is that you can run quiet, and then only relevant output will be printed to the terminal, as opposed to the entire header, including the list of GROMACS developers and other system-related information about the build. So it's doing some processing, setting up some of the data structures that will be used. So the values of the pole coordinate are provided in the GRO file. So let's see. So that's on these lines right here. So it's saying that they're starting off at about 3 angstroms apart, which is for heavy atoms forming a hydrogen bond. That sounds like a reasonable enough distance to have them apart. All right, so let's take a look at the data we've provided. So we're just going to look at the data in imd.log using grep. So grep is a very powerful tool. If you're not aware, you should spend some time familiarizing yourself with how to use grep at some point if you're going to be doing computational projects, because it's a very useful way to find lines in files, basically, on your file system, if you're looking for proverbial needles in haystacks, where you have lots of files in a complicated hierarchy, for instance, and you want to find all the lines that have a specific word. So in this case, we're just looking at one file, which we've given as an input to grep. And so it's saying that after 456 picoseconds, we decrease the update size, and then a similar size time interval, again, about 450 picoseconds, we're decreasing the update size again, and then, over longer times. And so here, covering is just an end-to-end transition across the sampling interval, which we put in our MDP file. So where is that defined? So AWH dim start is set as 0.25. So that's one end of the reaction coordinate, and AWH dim end is a sampling interval that's the other end of the reaction coordinate. So basically, we're going from 2.5 to 6.5 angstrom separation. Okay, so we can also see that the first transitions are faster than the later ones. So if you recall back to Berk's talk yesterday, you'll understand that the reason that this is happening is because initially you just want to get a rough and ready estimate of the free energy landscape. You want to make sure that you're covering the whole reaction coordinate, and so you basically are using a higher force to search the space initially, so that you can make sure that you go back and forth. And then once you have an idea of what it's going to take to get across the energy barrier of the transition, then if you want to actually have a converged energy, you need to add less and less force. And so this means that after the initial phase, the amount of force that is being added, in the AWH method is decreasing. Okay, so then yes, so that's actually said here. Yeah, so the overall update of the free energy denoted by, so this is fancy mathematical notation, which is saying the magnitude, so a scalar value of the delta F for the change in free energy is a free parameter in AWH. It's important because for these statistics to work out, you need the magnitude of the change, the induced change that you're doing as part of your method to, as t approaches infinity, magnitude of delta F should approach 0. So you need a time-dependent bias, basically. And so initially you need to have a magnitude large enough that the fluxions escape the free energy minima. But then later, so at first you have an exponential decay of 1 over e to the alpha t, and then later it decays as 1 over t, which is obviously much slower than 1 over e to the t, basically. So the initial stage is, can be referred to as a burn-in procedure, and it's designed to improve the robustness of the method. Okay, great. So there's a trajectory already found. So we'll look at the data in pull x.xvg. So here's what that looks like. It gives us some information about the executable and where it was run. Also when it was run in 2018. And then it has the actual data, which there's a lot of and is perhaps not so informative to us. So, well, what do we need to do? We actually need to do some analysis in order to make sure that this will work. So first we'll just define a function for reading XVGs. So executing this cell won't actually cause anything to happen because this is just defining the function. So then we'll actually try to plot the covering times. So we've got our function for reading XVGs. We will, supply the data. We'll use matplotlib, which is a super useful way to plot your data. And again, another thing, if you're not familiar with, you should probably take some time at some point to learn. I mean, you can certainly use this tutorial to help you out. And there's also, a great, basically suite of example scripts on the matplotlib documentation page that you can use to try to understand, how to plot any kind of wonky thing that you're interested in. So I won't go through this script too much because we're not so interested in learning about Python. So here is what the plot actually looks like. So you can see that initially we very rapidly go through the whole range of the reaction coordinate. So we're spending some time, and then eventually we've added enough energy, and now we're over here. And then in the second frame, I guess you could call it, of the reaction coordinate trajectory, we're doing the same thing, and then going eventually transitioning back over. And so those are very fast if you look compared to the other ones. So then it's much longer, and then it's changing times, and then the last one is very long. And the reason for that is going to be basically that as you get close to convergence, you're adding less and less energy, and so in each successive of the frames that are highlighted in black here, you're discovering finer details basically about the free energy landscape of the system that you're interested in. So this is also stated here where it's saying that so the X marks the exit time extracted from mdlog. So you can verify that these coincide roughly with the transition time seen in the trajectory. And then it just says basically what I've already said. All right, great. So, so there's some data already in the directory that you can use to, so we want to have some data to analyze using the tool called GMX AWH. So in the first cell, we'll list, try to list the contents of that directory, and we haven't created it yet. So, you'll get an error from AWS or from LS. So that's fine. So then we'll actually make the directory. and we'll run GMX AWH in that directory. So we'll use the EDR file, which contains various kinds of energy information, not just AWH, in the data directory, and then we'll output it into awh.xvg in awh-data. And so we're also, if you note, giving this -KT flag, yes, because the default in GROMACS is kilojoules per mole, but in this case, we've decided that perhaps it's more interesting to look at it in units of KT, in thermal units. All right, so let's look at the content of one of these files from after time 100 nanoseconds. So that's certainly after the first crossing, at least. Or wait, no, 100 nanoseconds is over here. Yes. Okay, so we'll run. I've already run that cell. So the processing is complete. So now if I run this, it's going to, again, show that we have extracted a large number of data, or a large amount of data. Oops. Sorry, the scroll wheel on my mouse is a bit inertial, let's say. Oh, actually, I haven't run this one yet. So let's run this guy, and now we have a nice plot. So this is showing the PMF along the reaction coordinates. This is basically in units of KT, so showing us the energy. So it's showing us that pretty close to where we started. So if you recall, I think we started about 0.31. Let's go back and look because I don't remember exactly what the value was there. And if there are any questions in the live document that are worth raising, I hope someone will jump in and just let me know. So
yeah, Berk is addressing the question now.
Oh, great.
Yeah.
Good to hear. All right, yes, so the starting position was around 3 angstroms. And so if we look at the plot of the PMF, we see that the free energy minima is actually slightly less than 3 angstrom, or 0.3 nanometers, and that you have to add and add and add energy until you get to a certain distance, and so you're basically breaking some hydrogen bonds as you're going up this line, and then eventually the hydrogen bonds are broken, but now you have some additional torsion energy probably is what's corresponding to, as you get even further apart, you get to some kind of minima, but the torsion energy is still not enough to compensate for the loss of the hydrogen bond, basically. So this is why, if this were a deeper well, we might expect that at equilibrium there was a more equivalent chance of finding the system in the 2 states. But since it's a relatively shallow well, this explains why we were able to say yesterday that there's a 10 power 4 energy difference in probabilities, basically. Okay, great.
Joe, there is a question that maybe might be of interest for everybody to hear the answer. So there is a question that, do you need multiple transition of the reaction coordinate, of simply one is enough?
Yeah, so that is a good question. So in general, you need multiple transitions. And so the reason for this is because you want to have statistics. You want to be able to say essentially something to the effect of, what is the average behavior of my system, when it is at a certain point along the reaction coordinate. So for instance, if I'm at 0.37, am I more likely to go up or down? And if I'm at 0.45, am I more likely to go up or down, and so forth. And in order to get those statistics and therefore some kind of confidence in what's going to happen, you need to visit those sites more than once, basically. So that's essentially why. And so this is actually, there's a related question sort of embedded in this question, which is, okay, so you know, in order to produce this one plot, you know, we need to visit the different sites multiple times to have some confidence in what the values are there. But actually, if we want to be really confident in what the values are, we actually need to do independent simulations and then average the plots together, so that we can say, you know, starting from, for instance, different starting positions or have these different initial velocities, does the PMF look very different, or does it look very similar? And then we can have some kind of confidence in the transition probabilities. So hopefully that has answered that question. Cool. All right, so now we're running less, which is just another terminal command to show us one of the XVG files. So it's going to say that, you know, there's some legend information, and then there is a bunch of data, which again, you know, we can't sort of interpret too much by looking at it. But we can learn about the legend from this handy table that's been produced. So column 1 is the PMF. So that's the free energy estimate along the reaction coordinate. So that's Xi is how I would pronounce that. Perhaps other people would pronounce it differently. Xi of X. So then there's the coordinate bias. So that's the bias acting on Xi. Note that Xi is attracted to large values of this bias function. The bias potential has opposite sign. So in column 3, we have the coordinate distribution, which is just a histogram. Then we have the reference value distribution, the target reference value distribution. So that's what we're actually trying to get to, which is, as Beck mentioned yesterday, is usually flat is our target, because we want to sample evenly across the whole space of the reaction coordinate. And then in the last column, we have the friction metric, which tells us something about the diffusion and can be helpful in pinpointing hard to sample regions. And so if you're really interested in specifically the transition state, you can look here and actually you know, go on to do further research to understand more information about the transition state, although that's an advanced topic, so we won't talk about it further here. So, all right. So what does this look like? So the first one is the reaction coordinate. It looks similar to what we already saw. So here's the target distribution. Here's what we're actually aiming for. Here is the distribution of the coordinates. Yeah, which, so 2 is the coordinate bias. So this is the biasing potential. So what you can see here is that you don't need to add much bias to the free energy minimum, which is also close to where we're starting the system. And then you're adding more bias as you want to get away from that. So the coordinate distribution, you know, it's just the histogram. The reference value distribution is the probability weight of the histogram. So this is saying something about how, let me see, how do I want to say this? This is saying something about how much energy you're adding to each of the points in your reference distribution. And then the friction is the one I was talking about a moment ago. So this is basically saying you have to add a bunch of energy to break a hydrogen bond. That's probably what's happening here. Perhaps there's another hydrogen bond, and then this energy is, yeah, perhaps some kind of torsional thing. So there are basically 3 places where the diffusion is somewhat restricted in your system. And if you're really interested in understanding the dynamics of your system as opposed to the free energy of your system, it would be very useful to investigate this further. Okay, so now we can do a sanity check. So the coordinate distribution and the reference value distribution should be fairly similar. So which ones were those? So 3 and 4. Yeah, they have similar shapes, I suppose. That looks reasonable. This is true everywhere in our case. Is an interesting question to ask. For the smallest distances where the atoms are repelling each other and the PMF is very steep, it doesn't hold. But such end effects are not critical. So, we're not particularly interested in the fact that it's actually very hard to get the system to. All right, interesting. I don't understand how I got muted.
Yeah. There is a question, Joe, if you want, since you stopped
Sure,
it.
sure.
Yeah.
Yes.
Was a request if you could go through again to the friction point?
Oh, sure. Yeah. So I think this is one of the more interesting outputs of the method, right? So, so in this case, we're studying the opening of a DNA base. And so we already have actually a pretty good insight into, what the energy barrier corresponds to, and it's the breaking of, one or more hydrogen bonds. And so the friction is basically saying something about where the system had the hardest time actually diffusing, basically. So if you look at the reference distribution, which is the probability weight histogram of the lambda value, you'll actually see, so that's this one here, you'll actually see that it is peaked around the same point that the friction is peaked. And so these things are related. They're not identical, obviously, but they're related by the fact that, if the reference distribution is having to spend a bunch of time, in a certain region, it's having to add more energy into that region in order to get basically equivalent sampling between all the different histograms. So basically, you could imagine, for example, that the histograms correspond to the little tick marks at the bottom of our plot here. And so, all that the right middle plot is saying is that in some of the histograms towards the middle, we had to spend a bunch of time and therefore probably add a bunch of energy, a bunch of bias, let's say, to the system. And so that's related to the friction, because the friction is the place where it is hardest to get uniform sampling, basically. And again, this is very interesting from the perspective of biology, because this is the transition state, biology, biochemistry, biophysics, whatever you want to call it. So this is corresponding to some kind of transition between states, basically. So I hope that is answering the question. Okay. All right, great. So we'll move on then. All right, so now we'll look at the evolution of the PMF estimate. So again, we're just going to look at some of our AWH files, and we're going to use matplotlib, which, as I mentioned, is extremely useful. And so now we're going to plot the distributions at various points. So in the first 1,000 picoseconds. Yes, so what is this saying? So it's saying that when we have not simulated at all, we have no PMF, which is not so surprising. We haven't collected any information about the system. We've learned nothing about the potential immune force. So at 100 picoseconds, which is the orange line, hopefully all of you can see it okay. It's saying we still actually haven't learned the full, or we have not spent so much time in perhaps in the full range of the system, because you can see that at 100 picoseconds, part of the system is flat. So this is a decent indication that we need more sampling, basically. And then at 200 picoseconds, we get to this green line, and then eventually we're converging down to the light blue line. So you may wonder, why basically, why do we see a jump from 100 picoseconds to 200 picoseconds and then eventually a drift that looks like it's sort of drifting back over the subsequent course of the simulation? And so this is related to the burn-in that we mentioned earlier. So we're getting a rough estimate of the PMF, and then we're kind of, well, you don't want to think of it as resetting it, but you know, we're putting progressively less weight basically on the initial part of you know, the bias potential that we've collected, and so you know, eventually we get back to something that looks fairly similar, although it doesn't have to be the case. Basically, you know, in this case, it's probably just that we made a pretty lucky starting guess. So there is something that it says you can do. You can increase the iStart variable to see how the PMFs are changing less and less over time. Note that this convergence does not easily translate into error estimates into the PMF. And to get such error bars, the simplest is to run multiple independent simulations. All right, so we've got iStart set to 0 here. Let's actually take its advice and set it to 2. Oops. All right, now starting from 200 picoseconds, we see something different. And so we do see that it is, you know, converging in a different way. Also, possibly that we have not looked at enough files. Yeah, interesting. All right, now we're having some fun. Cool. All right, so this is the really cool thing about Matplotlib and
Joe, sorry,
yes.
there is some delay in the connection. So when you modify something, wait a moment, because we see the things. First we hear you and then we see it.
Yes.
At least I
Yes.
I don't know the rest, but I just
Okay.
inform.
So thank you for that. Yeah. So what did I do? You know, I basically changed the start. So let's say we want to start from index 5 and go to index 25, not 55. Hopefully there are 25. And so, well, now it's a little too many things to actually see. But you know, now we're starting to get to a PMF that looks a little bit like the one we're expecting. So I'll even just put 1 here so that it's less. Yeah, great. So this is something you can play with more at home. But so yeah, as it says, congratulations. You know, now you're ready to run AWH simulations in GROMACS. So let's go back to the directory where we started and play around with a more advanced setup. And you know, I'll pause for any questions in case there are any questions about the initial part before we move on to the more advanced setup.
No, I think there is only one question that specific asks a reaction coordinate for a specific system, but I think it's not very inherent now for this.
It's a little,
yeah.
So
it's a big challenge, the reaction coordinate. Yeah, but then it's not. So then I think from what is in the live document, I think you can proceed. All the other questions were addressed.
Okay, great. So I will say actually one thing here about the reaction coordinate. So you know, when you run, you know, you'll typically, you know, if you've picked a good reaction coordinate, you will find that your system looks like it's converging. Sometimes your system will converge to a PMF, and for reasons that you know, that I can't really elaborate on, that PMF might look a little bit suspicious or wonky to you. And so one thing that you can do in such a situation is actually look at what the difference between, you know, so for instance, you may have started from, you know, some from one place or another. And so sometimes you can actually do a little bit better by changing your reaction coordinate based on the information gained in an initial PMF. So you may have thought, oh, you know, I need to sample this range, or, you know, I need to focus on, you know, such and such part of the system. And you might realize, oh, you know, the reaction coordinate is being sampled in some kind of weird way. And so this is usually some kind of indication that your reaction coordinate is either not fully capturing the transition that you're interested in, or alternatively that you've not sampled long enough to capture the transition that you're interested in. So in AWH, the second part is less of an issue because generally it will, it's not so hard to monitor the convergence and figure it out. But if you have not picked an optimal reaction coordinate, sometimes you might need to go back to the drawing board and change a little bit what that reaction coordinate is, possibly based on information you get from an initial, free energy calculation. Okay, so now we're going to do some bias sharing walkers. So if you want to get an increased performance, an easy thing to do is to parallelize the sampling using multiple walkers. So these share a common bias, and they can reduce the length of the initial stage significantly. So you just need to run GROMACS MD run minus multi-dir with TPR files to launch the simulation. So now we're CDing out of the AWH single directory and into the AWH multi-directory, and we're just listing the contents. So we've got our force field, we've got our MDP, we've got our confirmation file, we've got some data, we've got an index file, and we've got a top. So again, so let's see what the differences are between the simple MDP file and the multi-MDP file using, again, a diff. So the differences between the two AWH simulation files are smaller than the difference between the equilibration and the AWH file. So, of course, we've been thoughtful and given them different and informative titles. In the AWH simulation, we've needed to sample longer because we only have one simulation. And in the multi-case, we can sample for each replicate an order of magnitude less time, which means that in this case, we will be sampling, for a total time, so 4 times this, which should be 1/5 basically of the simulation time in the single case. So this is a pretty nice speed up, that's generally hard to get. And, we're usually interested in fastest time to problem solution. So this is very nice. Okay, so as it says here, the AWH multisim is just a switch to turn on the multisim sharing. So it's asking this question: what is AWH1 share group? And so this is an important concept. So each bias has to share its information with another bias. And so in this case, we only have one biasing group. So it's just the distance between the two nitrogen atoms that we defined, using the index file that we have. But if, for instance, you had you wanted to do a 2-dimensional landscape, you would need to specify which walkers are walking along which dimensions of your landscape, basically. So that's all that this is saying here. That we need to remove the ambiguity. So we've also switched on AWH equilibrate histogram, which you can see, here. And so that's, as the comment says, ensuring that the histogram is close to the target before decreasing the update size. Yes. So from a user perspective, the main difference is now that the input has been multiplied by the number of walkers. Okay, so let's look at the data that we've been given. So what have we got? What have we got? Not very informative, right? There we go. The contents of these directories are as follows. So in data 0, so here are the contents. So here are the contents of the directories, which are helpfully named 0 and 1. if we want to learn about how the data was generated, we can look at the log file in one of the directories, which is telling us it was using GMX MPI with various parameters, most of which are related to performance, except for the multi-tier, which is a required input in this case. Yes?
Sorry, Joe, there is a question. Why the output is more, why we output more often, but I think it's other way around. If you can go up to the MDP parameter.
Yes, so that's a very good question, very perceptive. So in fact, we are outputting more often in the multiple Walker case. Yes, you'll see that we're outputting 100 times more often. And so the reason for that should basically be that we expect a super linear scaling, basically from having multiple walkers. So if we want to have a good handle basically on the free energy landscape, we need to have collected data at more points. If we were using the same output frequency, the system would actually sort of evolve too fast for us to collect the data we're interested in. So that's why we've had to increase the output frequency. So hopefully that answers that question. Okay, so the initial stage for multiple walkers. So we can do a very similar analysis as we did in the single walker case. And again, this is the same system, this is the same DNA hairpin, and we're just trying to figure out the PMF of opening one of the DNA bases using the reaction coordinate of distance between two nitrogen atoms. So here we can see the first covering is in 68 picoseconds, which if you remember in the single walker case, the first covering was in, I believe, 900 picoseconds. So this is much faster. So it's saying that it's equilibrated after 226 picoseconds. And at that point, it's going to the sort of production run, you can think of it, where it's collecting the statistics that it's going to need in order to actually estimate your PMF. So you can, as it says here, the free energy update size decreases more rapidly because as the interval is now covered cooperatively by all of the walkers. All right, so now we're going to do some more plotting. So I'm just going to go ahead and run this, and then we'll spend some time walking through it. All right, so the dash line, as it says down here, is denotes the first actual covering. So you can see, so it looks like maybe only 2 of the walkers are plotted. Yeah, so there actually only are 2 walkers. That's right. And so you can see that at least one of the systems has managed to cross the full range of the reaction coordinate by the time we reach the dotted line. So this is similar to what has happened in the single walker case, but it's happened much faster because the 2 different walkers have been focusing on basically the region around where it started, and then one of them is able to escape faster. And once one of them escapes, then we've got a covering, and so now we can actually move on and try to generate further coverings. So we've got this leading question here: is the histogram still biased by the initial conditions at this time? And so I would say once you reach this time, the system is no longer biased, right? Because you have covered the full reaction coordinate. So, we set AWH1 equilibrate histogram equals true in the MDP file. And so this means that the detection of the covering won't take effect until the accumulated shared histogram has become uniform enough. So this is actually happening at the first solid line. So at that point, So, you know, at the first covering, sorry, I think I misspoke a little bit. At the first covering, you know, we have sampled the system, but we've not uniformly sampled the system. And so that's only happening once we get to the first solid line. And so pre-equilibrating the histogram in this way is nothing but a heuristic that spreads around the walkers and helps them lose the memory of the initial configuration before trying to converge the free energy. So now we can verify also that a covering is not equal to a full end-to-end transition in a single walker case, because only all of the walkers together need to do a full covering, not any individual walker. And so just to summarize, running multiple walkers has the potential to improve the initial convergence. But do remember that in order to actually obtain statistical error estimates, you need to run multiple multi-walker simulations and then average those together. So this has actually gone fairly faster, I think, than we had a lot of time for. But so then now we have a lot of time for questions, or if people want me to go through specific parts again, surely we can do so.
Yeah, thank you, Joe. I think maybe you can say something more on reaction coordinate, which type of reaction coordinate people can use, because there was a question that was asking that was answered, an example of the dihedral angle, but maybe you can just say all the range of the reaction coordinate that can be used. Yeah.
Sure. So there's a lot of ranges of reaction coordinates that can be used. I wouldn't say that your imagination is the limit, because there are certainly reaction coordinates that you could come up with that are probably not so useful to use. But in general, you know, one tip I think that is useful to keep in mind when you're trying to come up with a reaction coordinate is that, you know, it is helpful, although not required, if the reaction coordinate is something that you can have kind of an intuitive understanding of, you know, at a chemical or physical or biological level. So this is, again, not a requirement, not something that you must have, but, you know, the ultimate goal is to, you know, so I'll scroll back a little bit. The ultimate goal is to, you know, have a nice looking PMF that looks like this one we've got here. And if, you know, so a reaction coordinate can be, at least in GROMACS 2022, you know, which will come out in 2022, you know, we've added support for writing general functions of the coordinates. So, you know, you could imagine having, in addition to the distance of two particles, you know, you could use the center of mass, and that actually already is possible in GROMACS. You know, you could imagine basically defining vectors that correspond to, you know, the sort of opening and closing of, you know, some, you know, Pac-Man shaped protein, for instance. And this could be a reaction coordinate, you know, that could give you some kind of interesting information. You know, another example is, so you may have an alpha helix that from previous experiments such as X-ray crystallography, or, you know, wherever the data comes from, you may know that a specific alpha helix, you know, if it's rotating, you know, 15 degrees or something, that this corresponds to some structural transition, and you may want to just move this alpha helix and then see what else happens, or you want to may move this alpha helix and correspond and have a second dimension to your reaction coordinate. You know, that's some other property of your system that you also think is biologically relevant. But you know, again, it's important to keep in mind that, you know, while you can come up with arbitrary parts of your system to, you know, use as a reaction coordinate at the end of the day, you know, if you don't understand, you know, what it means. So let's say you have 3 alpha helices in your protein, and they all move 15 degrees, you know, in some you know, coordinated structural transition. So if you try to simulate the system with a reaction coordinate that's one linear combination of the degree shift in all 3 of these, you know, you may get a free energy landscape, you may get a PMF, but how are you supposed to learn anything about your system based on the fact that all 3 of them have, moved a certain amount. In that case, it's a little similar to RMSD. So you've learned something, but you can't really relate the things you've learned to other things that you might know. So it's in general very challenging, I would say, to pick a reaction coordinate. The best thing to do is to go into the literature and try to understand the biology of your system, and to play around a little bit. You may have some initial ideas of things that can be good, and maybe these ideas will just work, and maybe you'll be extremely unfortunate. So an example of an intuitive reaction coordinate that's wrong is you could be interested in studying salt, so sodium chloride, NaCl. And so you may think to yourself, aha, I know exactly what to do if I want to understand the behavior of salt in water. I'll pick a reaction coordinate, which is the distance between the sodium and chloride atoms. And if you do this, you will get a not very good looking PMF, because it turns out in this case, the reaction coordinate that is relevant is basically the hydration coordination number of the number of water molecules that can access the sodium chloride molecules. And so, yeah, so basically this is just to give a little bit of warning that you generally will need to play around and have a good understanding of your system, and that even if you have a good understanding of your system, there might be other details which you need to consider that cause the reaction coordinate that you think makes sense to not make sense. So yeah, I don't know, Alessandra, Berk, do you guys want to say more about this topic?
No, but I have another question. I think one thing that from the reaction coordinate, we can say that all the reaction coordinate implemented for the pool code are usable in
Yes.
AWH. So that is
Yes.
also for a general user purpose. So the user know that. And there is a new question. Multiple Walker mean multiple CPU also?
Yes, so this is up to you to determine, basically. So in general, it should mean multiple, at least multiple cores on your CPU. It depends on the size of your system and how powerful your CPU is. But yeah, so you can, this is basically a free parameter that you will need to choose. Probably you will get terrible performance if you try to run 2 simulations on the same core, unless you have an extremely small system, in which case you're probably not that interested in it. But in principle, it's possible, although generally, in the case of multiple walkers, it's the same as in the case of, in general, if you're running in these simulations, you're not just running one, you're running in triplicate or maybe even, in quintuplicate to be able to get good statistics. And you generally, how would you do that? If they're completely independent, you would probably submit them, as Slurm jobs, or as batch jobs on your local cluster, which Mark talked about a little bit in his talk earlier. So the main difference with the multiple walkers is that you would need to have one script that submits all the jobs, because you need to make sure that they're actually running at the same time.
Yeah, there is another question, but it's more a general one. Someone asked if people can use or reuse the Jupyter notebook. So the Jupyter notebook that we have provided can be used and reused. Maybe you can show Joe the web page of the tutorial web page.
Yes,
there we have
good.
the license under which we distribute those Jupyter notebook.
Oh, come on.
So the page is tutorials.gromacs.org.
There we go. Yeah, so one more time. Oh, no, not far enough, or too far. Oh, I think I just need to go to the table of contents. All right, so here are the available tutorials. So we went through the introduction to molecular dynamics yesterday. Just now we've been going through the accelerated weight histogram. So we also have one for umbrella sampling and another for free energy of solvation. So these have been developed as part of work by BioExcel and in CCS, which is where Mark Abraham works. So Alessandra, is there another tutorial that we're hoping to land soon?
Yeah, there will be a new tutorial, but what I was meaning, if people will use those, they have to fulfill the license. So we have a licensing, you see? Yeah, so people can reuse the tutorial.
Yes.
Just that it's important that you acknowledge who has done it, and yeah, you count that where they come from. But for the rest, everybody can use and do what they want. We have new tutorial coming up. I plan to build one on the free energy using accelerated weight histogram. And probably there will come one next year on density fitting.
On, sorry, what was that?
Density fitting.
Density fitting. Oh yeah, that'll be really nice.
Yeah, so that is on the pipe. Those two, the solution free energy, and then we will also have a replica exchange that will also come soon. And a binding free energy, that is also. So these are all the one in pipeline.
So that's really exciting. So do watch this space, tutorials.gromacs.org, because as Alessandra said, we're hoping to have many more tutorials coming in the future. So if your particular work case is not covered by any available tutorials, perhaps if you check back in a few months, we'll have new tutorials that might give you some insight into what you want to do. And of course, if you can't find a tutorial on our website, there are other tutorials. So there's Justin Lemkuhl's GROMACS tutorial, which is sort of a classic in the field, I can say. And so there's some great tutorials there that are not working as Python notebooks, unless they've been updated recently, and that I'm not aware of. But they're still useful to work through. Were there other questions?
So there was one other thing that I thought maybe was worth to discuss. Let me see. Yeah, maybe you can, there was a question that do we need, it was answered, but maybe it's of a general interest. Do we need to keep the distance between pool groups less than half of the box size?
Yes, I believe for efficiency reasons, you need to.
For physics and maths reason. Because otherwise
yeah.
So
yeah, so it's a repeated box. So if it's basically you can't have it longer than half the box length because it'll just be close to another neighbor. So this could cause issues because then there's additional bookkeeping, which maybe we don't do. I don't know. I've never tried this, and I remember that there are occasionally issues here. So yes, generally it's a good idea to not do that, I would say.
So yeah, I think I don't see any further question. Yeah. So I think all the one has been